All right, let's do a little more probability. Okay, let's look at some conditional probability. So this is from section 11.3, find conditional probabilities. There's several examples of ones you need to do given to you on the study guide. So let's look at this question that was on the test. Okay, what's the probability? The conditional probability would actually be that. But so if we have the set of numbers from 1 to 15, and I want the probability of B, then what I would be doing is looking at how, okay, first, I would be thinking about these numbers all the way. Let me write them all out. 8, 9, 10, 11, 12, 13, 14, and 15. So like the event A would be that the number's odd. So that would be 1, 3, 5, 7, 9, 11, 13, and 15, right? Those numbers. Okay, B is that the number is a multiple of 3. So that would be 3, 6, 9, 12, or 15. Okay, so the probability of B happening would be 1, 2, 3, 4, 5 out of the 15 numbers, which reduces to be 1/3. But this is the probability of B given A. Okay, so what that means is that I'm going to actually be reducing my sample now, my sample space, my starting sample, rather than it being all the numbers from 1 to 15. I want the probability of getting a multiple of 3 given the number is odd. So I'm actually going to be using this as my denominator. So out of these numbers, the multiples of 3 would have been just 3, 9 is a multiple of 3, and so is 15. So there would be 3 multiples of 3, not out of 15 this time, but out of all the odd ones, which is 1, 2, 3, 4, 5, 6, 7, 8. So that'd be 3 out of 8. So that's how you do it. So that given piece, the probability of B given A, that means you just are going to restrict your the numbers under consideration to be those that are odd, and then you're going to see how many multiples of 3 there are in that. Okay, here's another conditional probability. This was question 2 on the test. Well, it's kind of confusing. It was actually question 4 on the test, but I had misnumbered the problems. So let me just erase that. So this is also probability. We want the probability that the second card, you're going to draw 2 cards, deal 2 cards without replacement. So 2 cards dealt, and that's without replacement. You're not putting them back in. That's what makes it conditional probability. Okay. So this one says, what's the probability the second card is a 4 given the first one is a 4? So it's like I'm still thinking this. So the first one is a 4 here. So I know I got a 4 on that one. Now the probability of the first one being a 4 would be 4 out of the 52, one of each suit. But what they want, the answer to the question is just whatever goes there. What's the probability the second card is a 4 if you got a 4 the first time around? Well, you're not replacing. So there's now going to be only 3 4s left and only 51 cards left. So the answer would have been 3 out of 51. Okay. And it's just that just this is all you want. Okay. All right. Then the other part I asked on that is, what's the probability the first card is a heart and the second card is red? Okay, so for the first card to be a heart, there are 13 hearts in those 52 cards. It's the first one I'm getting, so all of them are available. But when I go to do the second card, I only have 51 cards left. And I'm wondering what the probability is that the second card is red. We're assuming the first card was a heart, which is red. So there's 26 red cards normally, but there's only going to be 25 available. And the answer isn't just the 25 out of 51, because it wanted the probability of the first card being a heart and the second card being red. So you would multiply those. And when you do and you simplify everything, you wind up with 25 over 204. Now, if they had worded it, what's the probability that the second card is red given, given the first was a heart? That's a different question. That would have been just 25 out of 51. Okay. All right. And then, I passed out that deer problem in class because there was a question that talked about using a probability tree with conditional probability. So look at the example 10. So look at example 10 in the text with Ray and Tom, and look at the part of the solution that had the tree diagram in it. That would be another example besides the deer problem I'm about to do. Okay. And that would be from section 11.3. Okay. But let's go ahead and look at the deer problem that I passed out in class. Let's see, I have it somewhere. Here it is. All right. So we have a situation. Let me see if I can copy that. I want that to be copied and put it on my word sheet real quick. Okay, yeah. All right, so here's the deer problem. All right, so this is kind of an interesting and pretty relevant little problem. So it was a good problem, and there's a reason I'm doing it. So you should really pay attention. So here we have deer that have contracted a disease. There's a test for it, but it's just not 100% reliable. So we have deer that are diseased and those that aren't. And then we've got all these statements that we have to consider. And the question was to use a tree diagram to answer the following questions. What's the probability that a deer in this population tests positive? And then what proportion of those testing positive have the disease? So this came from a problem I found on the internet, and I really liked it. And for another example, look at example 10 on pages 630 and 631. That's a similar situation. All right. So as we do this, what we're going to think about is how the deer might have the disease or not. Okay. And maybe I could use the little not symbol for that, but I'm going to say deer diseased or healthy. Okay. All right. Now, as you read through this statement right here says it is known that 20% of the population has the disease. So I can use a tree diagram to help me get this figured out. I need a little more room. I'm going to move this down just a bit. I need just a little more room there. So diseased or healthy. I know that 20% of the population that we're looking at has the disease. Okay, that was this statement right here, which means 80% would not have it. Okay, so 20% did, 80% didn't. All right, then let's go to the first bullet, which says if a deer has the disease, so that's this first branch, it will test positive 95% of the time. So some of them are going to test positive, some are going to test negative. We're not talking about whether they actually have the disease or not. We know they do. We're just indicating whether the test was positive or not. So if a deer has the disease, it will test positive 95% of the time. So 95% of the time. I mean, it should be 100%. They have the disease, but the test is not 100% reliable, is it? So if they have the disease and 95% test positive, then that means 5% are going to test negative. They have the disease, but the test doesn't show it. Okay. So think about that. Then the next bullet says, if the deer doesn't have the disease, it will test negative 90% of the time. Okay, you'd expect it to test negative 100% of the time. So if it didn't have the disease, it should test negative. But it says it only tests negative 90% of the time, which means even though it doesn't have the disease, it's healthy, it will test positive 10% of the time. Okay? So you get some false positives and you get some false negatives, right? This is like a false negative. This is like a false positive. These were ones that were down here. These were healthy deer that still tested positive even though they weren't. Okay, think about COVID testing. Same things happens with that, just with various percentages. Okay, so what we could do, shoot, I need a calculator. So what we'll do now is we'll consider the four possibilities. Having the disease, testing positive, having the disease, testing negative, not being healthy and testing positive, not having the disease and testing positive, or not having the disease and testing negative. Let me find my phone. I can do the calculations there. All right, so let me get the probabilities for each of these cases. All right, so let me go over here to my calculator and just multiply those. So this would be 0.20 times 0.95, 0.20 times 0.95, and that would be 0.19. And then 0.20 times 0.05. See how I'm following the branches and just multiplying? 0.20 times 0.05. That gives me 0.01. 0.80 times 0.10 gives me 0.08. And then 0.80 times 0.90, and that would give me 0.72. Okay. All right. So now we got some of the data. Let's see what the questions are they're asking me. What's the probability that a deer in this population tests positive? Probability that we get a positive test. Didn't say anything about whether the deer actually had the disease or not. Positive test would be 0.19. Here's positive, plus the 0.08. So the 0.19 plus the 0.08. So that would be 0.27. So there's a 27% chance that a deer in this population would test positive. And then it said, what proportion of those testing positive actually have the disease? What proportion of those testing positive actually have the disease? So that's the proportion of those testing positive that actually have the disease. It's like this would be the denominator. Okay. And see, the proportion of those testing positive that have the disease, see, these are the two groups that tested positive. This is the one that actually had the disease. Okay. So that would be 19, the proportion would be 19 out of 27 would be the proportion of those testing positive that have the disease. So that would be that second question. So that's the first question. That's the second one. Okay. So I wanted you just to see an example of how you could use those tree diagrams along with your probability to figure out the answer to questions like this. And you just follow along those branches, right? And multiply. It's like an and. The probability of having the disease and testing positive, it's a multiplication. Okay. And then the adding happened because we were then looking at the situation of the deer that tested positive, and there were two here that fit that condition. So we would add those to get the 0.27. Okay. So that kind of ends the conditional probability ones. And then we also on that test did the binomial probability formula. Okay, so let's do a couple of those. Binomial probability formula. And you'll have the formula. Just got to know how to use it, how to set it up. So it's the probability of this many successes Okay. And we know that that equaled n choose x, probability of success raised to the x power, probability of a failure raised to the rest, the n minus x. Okay. So some questions we had on that would be ones like a coin is tossed 6 times. This is question number 3. Okay, a coin is tossed 6 times. Find the probability that exactly 2 are tails. Coin tossed 6 times. Coin tossed 6 times. What's the probability exactly 2 are tails? Okay, so getting a tail would be a success. Okay, so x equals getting, or a success equals, let me put it that way. Success is getting tails. So the probability of 2 of those happening would, out of 6 tosses of the coin, would be 6 tosses. You want 2 successes. You have a 1 out of 2 chance. The probability of getting tails is 1/2. You want that to happen twice. The probability of not getting tails would be the rest. That would be 1/2. And the remaining 4 possibilities. So when you do that and you work it all out, you'll wind up getting 15/64. Okay. All right. And the examples that they gave on this in the study guide did not include the ones that were kind of tricky that said no more than 3 are tails, where you'd have a lot of those to do. So I think we're okay just looking at that one. But let's look at one more. Let's look at question number 4. So this was 3A. Number 4 said a prescription drug is known to produce undesirable side effects in 25% of all patients. Undesirable side effects. And the probability of that happening was going to be in 25% of the patients who use the drug. Then you're sampling 9 patients. So in a sample of 9, find the probability that exactly 3 have undesirable side effects. Exactly 3 having undesirable side effects. Okay. All right, so I wanted to look at this one because I wanted to look at one where these probabilities weren't the same. So we have 9 in our sample. Let me start off this way. We want the probability of exactly 3 successes. We have 9 in our sample, and we're going to choose then 3. We're going to consider a success being getting the undesirable side effects. That'd be a success because of what we're looking for. We're looking for the probability of getting undesirable side effects. So the probability of getting undesirable side effects would be 0.25. Okay, we want to know the probability of that happening 3 times. So we put a 3 there. So the probability of not having undesirable side effects would be 75% of the time, 0.75. And that would be true for the remaining 6 people. And then you work that out. And when you do, you get I think that's right, 0.234. Okay. All right, so that covers the conditional probability objective, which is 11.3. And then it also covers what they said for 11.4, calculating a probability using the binomial probability formula and then applying the binomial probability formula.